Okay. The next variation is we want to obtain the volume of the we want to obtain the volume of a solid of revolution that involves revolving a region around a vertical axis instead of a horizontal axis. If you notice, we've been revolving only around vertical axes, whether it's the x-axis or other horizontal lines. So what we're going to do is take this blue region and revolve it around the y-axis. So the thing to note here is that when I was doing this in the x direction, let me just temporarily, actually I'll just draw another line here. Imagine this is the x-axis. What I was doing was I was finding washers that looked sort of like this. So they were either discs, or maybe they had a hole in the middle. They were washers, and their thickness was dx. But if I'm revolving around, that's what happens when you revolve a curve around a horizontal axis. But if I revolve a curve around a vertical axis, what I'm doing is I have some curve like this, and I'm forming either discs or washers that look like that. So they stack now in the vertical direction, and their thickness is dy. So I'll just write the dy over here so that it doesn't clutter up that area. So that's dy. So if you're revolving around a vertical axis using the disk or washer method, you have to use an integral in the y direction. Now, I want to be a little careful about what information I give out here, because some of you are going to say, okay, how do I know this? I already know that many of you are thinking, I will never understand this geometry. Can you just give me the formula? No, there's no way to do this without understanding the geometry. The so when I say that you have to use the variable y when you have a vertical axis with the disk washer method, all of those conditions are necessary. In the next section, we're going to learn a different way of finding volume of revolution, where which variable you use is going to switch depending on whether it's horizontal or vertical. So it's a whole other bit of geometry you have to learn. But in any event, right now, since we're covering the disk washer method, if you revolve around a vertical axis for now, you would use the variable y. Okay, so let's take a look back at the blue region and see what the washers look like. So what we have is we're revolving around the y-axis, and what we can see is that the circle is going to look, let me draw it in red like this. We're going to form a circle that looks like this, and it's going to have a thickness of dy. Now, what's the radius of that circle? The radius of that circle is just going to be that horizontal distance. So that's going to be really just right minus left, where the left curve is very easy to spot. It's the y-axis, where x equals 0. The right curve, we have y as a function of x. I'm going to need to write x as a function of y. That's fairly easy to do here. X is just equal to y squared. So this horizontal distance, which gives the radius, there's only one radius. There's no hole in the middle of this disk. So this is going to be the radius is equal to y squared. All right, so easy enough. So we can see that the area, let's form the integral now. Form the integral. First of all, let's put a pi outside the integral because we know there's going to be a circle. Actually, let's do it the classic way, and let's put the pi inside. So we get the area of the circle, which is pi times the radius squared, so that's y squared squared, and multiplied by its thickness. Now we just need to know what the interval of integration is. Well, what we have here, the top boundary is the line y equals 2, and I've put in where it intersects, is this curve y equals x squared is going to intersect y equals 2 at the with the x value of 4, so this is the point 2, 4. What we can see is the upper boundary of this region is 2. Now some of you I know are going to want to say that the boundary should be 0 to 4, but that's because I know everybody naturally thinks in the x direction. We're doing this in the y direction. The limits of integration are the lowest possible y value going up to the highest possible y value, so they are 0 to 2. So that's the integral that gives the volume of that blue region. Okay, we're going to do a similar problem. It's a problem involving the same curves, but we're going to change it up a little bit more. So we're going to find the volume of the solid obtained by revolving the green region. This is now the region below y equals x squared, but equals square root of x instead of the region above it. Find the volume obtained by revolving that green region around the line x equals -2. So once again, we're expanding what sort of volumes we can find by changing the axis from one of the x or y axes now to just an arbitrary vertical line in this case. So once again, let's draw what the circle looks like. So we can see that the close part to the line x equals -2 is this, and the far part is given by this vertical line x equals 4. So what we can see is, and by the way, let me just show you this trick. I know I covered this in last week's workshop, but in order to find what the left and right curves are, because I know this ends up being very confusing for people when they're doing this in the y direction, draw a horizontal line and focus not on the x values of the points that you find, but rather which curves are being intersected. And what you can see very easily when you do this is that on the right side you intersect the curve. Remember, a line is a curve. You intersect the curve x equals 4, and on the left side you intersect this curve that we can write as either y equals square root of x, or since we're going to do this in the y direction, we'll write it as x equals y squared. It's the same curve, at least in that part of the plane. So that's what tells you which ones are the right and left curves, is which ones intersect this horizontal line on the right and left when you draw that. So what we can see is that the right curve is x equals 4 and the left curve is x equals y squared. So what I do is, to find the radius, we can see that the horizontal distance between that curve and the line x equals 2 is going to give us the inner radius. So the small radius is just going to be, it's going to be this point on the right. This is this curve on the right. So y squared minus -2, which equals y squared plus 2. And the outer radius, given by this blue line, is just going to be the distance from this vertical line 4 to this vertical line -2. So I'll write that here. The outer radius is just going to be 4 minus -2, which equals 6. So we form the integral. The integral is just going to be pi times the integral. We know that the lowest possible y value is down here, which is 0, and the highest possible y value in this green region is given by the line y equals y equals +2. So I integrate from 0 up to 2. And now I'm going to do the outer radius squared minus the inner radius squared. So the outer radius is just a constant of 6. So I take 6 squared. And the inner radius is y squared plus 4. And I square that. And I get dy, like that. Okay. So there's yet another example of the washer method.